Welcome everyone to today's explainer on software engineering. We're diving straight into section 9.1, evolution processes. It's really easy to think that once you launch a system, your job is done. But as you're going to realize today, deploying a system isn't the end of the journey. It's literally just the beginning. Let's get right into it.
Here is our game plan for today. We'll start with an introduction to software evolution, then compare evolution versus servicing. After that, we'll map out the actual evolution process, talk about the dangers of emergency repairs, look at agile versus plan-based handovers, and finally, wrap up with a summary and exam focus.
All right, part 1, Introduction to Software Evolution and the Reality of a Software's Long-Term Lifespan.
When you're first learning to code, you kind of just build a project, finish it, and move on, right? Well, in the professional world, software is never just written once and forgotten. Get this, up to 90% of a company's software budget goes toward evolution, not new development. That's a massive chunk. Historical data shows somewhere between 60 to 90% of costs are tied up in maintaining and evolving existing systems. Actually, at any given moment, about 75% of developers are working on software evolution. Businesses absolutely have to keep investing in their code to ensure they keep getting value out of these massive assets.
So, let's officially define what we're talking about. Software evolution is the ongoing process of changing and updating a software system after its initial release just to keep it useful. Think about massive programs like Microsoft Word, or those giant banking systems handling our money. They last for decades. And over time, business needs change and user expectations shift. To survive, parts of the software have to be modified, whether that's correcting errors, adapting to new hardware, or adding features to fight off competitors.
This spiral model perfectly illustrates how we should picture this life cycle. You can see 4 main quadrants here: specification, implementation, validation, and operation. You start by looping through these to build release 1 of your system. But once that's delivered, new changes are proposed almost immediately, and you spiral right back out through those exact same 4 phases for release 2. In today's fast-paced world, the gap between these releases might literally just be a few weeks. It's a continuous, never-ending spiral that goes on throughout the program's entire life.
Moving on to part 2, evolution versus servicing, looking specifically at Roglic and Bennett's lifecycle model.
Now, while that spiral model assumes a really seamless transition from one release to the next, custom business software usually follows a slightly different path as it ages. Roglic and Bennett map this out. Looking at this timeline, you can see the journey goes from initial software development into software evolution, overlapping into software servicing, and finally hitting software retirement. Over time, as a program gets older, the way we actually handle the code fundamentally shifts.
The absolute most crucial thing here is understanding the difference between those 2 middle phases. During the evolution phase, the software is being heavily modified. The team is adding major features, maybe even changing the underlying architecture. But as the code is repeatedly tweaked over the years, its structure naturally degrades. Adding new features becomes way too expensive. That is when the software transitions into the servicing phase. Here, the program is still useful, but we completely stop making major structural changes. We're only doing small, essential, tactical stuff, like critical bug fixes. We aren't evolving it anymore, we're basically just keeping it on life support.
Which brings us to the end of the line, software retirement. This is exactly what it sounds like, the final stage where the software is permanently taken out of use. Towards the end of that servicing phase we just talked about, users often just have to figure out workarounds for bugs, because fixing the code just isn't cost-effective anymore. Eventually, the whole thing is retired, which actually costs money too, since you have to safely transfer all that essential data over to whatever new system is taking its place.
All right, part 3, the evolution process. Let's look at a cyclical approach to managing system changes.
Now that we've looked at the macro timeline, let's zoom in on the actual step-by-step process of making a single change to an active system. Everything starts with a change proposal. Maybe it's a bug report from a user, a new feature request from the marketing team, or just a cool idea from the devs. That proposal triggers the change identification process, which feeds directly into the software evolution process, ultimately spitting out a new system release. And this cycle just keeps spinning relentlessly throughout the program's life.
Breaking that evolution process down, we're looking at 4 vital steps. First up, change proposals. That's gathering all those requests and bug reports. Second is impact analysis. This is super important. It's where you look at the code and ask, okay, how much of the system is this going to affect? What's going to break? And how much is this going to cost to implement? Third is release planning, where you filter through those proposals and decide exactly what makes the cut for the next version. And finally, step 4, change implementation, designing, coding, testing, and getting that new release out the door.
But there's a really big hidden hurdle inside that final implementation step, especially if a new team is taking over old code. It's called program understanding. This is that initial phase where developers literally just have to figure out how the existing program is structured and how it actually works. For legacy systems, this is by far the hardest part of the job. You have to grasp the existing logic completely. Otherwise, when you drop your new code in, you'll accidentally introduce new bugs and totally wreck the existing expected behavior.
Moving on to part 4, emergency repairs. Basically, what happens when things go critically wrong. Up until now, we've talked about this nice, standard, well-planned evolution process. But let's be real, software engineering doesn't always go to plan. Ask yourself, what do you do when a massive security flaw or a critical bug pops up at 2 a.m.? You definitely don't have time for a 2-week impact analysis and careful release planning. You have to do a rapid emergency fix. This means developers apply fixes directly to the source code to solve the immediate fire, completely bypassing the normal procedure of updating requirements and design documents first.
There are usually 3 main reasons developers are forced to make these terrifying unplanned changes. 1, a serious system fault or security vulnerability brings normal operations to a dead stop. 2, unexpected disruptions in your operating environment, like a crucial third-party server suddenly going down. Or 3, unanticipated business changes, like a sudden new government regulation that dictates the system has to legally behave differently by tomorrow morning.
But here is the massive danger with emergency repairs. When you hack the source code directly without updating your design models, your code and your documentation instantly fall out of sync. Sure, the intention is always, oh, I'll go back and document this tomorrow, but then another emergency happens, the original change gets forgotten, and suddenly your documentation is completely untrustworthy. This heavily accelerates the software's aging process. It makes future programming understanding a total nightmare, and means any future evolution is going to be significantly harder and way more expensive. You're supposed to refactor that emergency code later, but honestly, that almost always gets skipped.
Part 5, Agile versus plan-based handovers and the frictions in team transitions.
So we've seen how undocumented repairs cause headaches down the line. Now let's look at another common pitfall, team handovers. Often, the team that builds the software isn't the one maintaining it. And, depending on the methodologies these teams use, this transition can be incredibly painful. Let's contrast 2 problematic scenarios. First, imagine an Agile development team handing a project over to a plan-based maintenance team. That plan-based team is expecting thick, detailed documentation to guide them. But Agile favors working code over heavy docs, right? There might not even be a definitive list of system requirements. On the flip side, what if a plan-based team hands over to an Agile team? The Agile folks are expecting simplified, clean code with a robust suite of automated tests for their fast-paced sprints. But a plan-based system probably doesn't have those automated regression tests, and the code might be super rigid. That Agile team is going to have to spend a massive amount of time just re-engineering the code and building tests from scratch before they can even start their normal workflow.
Finally, Part 6, Summary and Exam Focus. Let's look at the essential takeaways for your next test. We've covered a ton of ground today, from the macro lifecycle down to the nitty-gritty of handovers. Here are the 4 absolute essentials you need to lock in for your exams. Number 1, up to 90% of a software budget goes to evolution, not the initial build. Number 2, you've got to know the difference between the evolution phase, where we make heavy architectural changes and add features, and the servicing phase, where the program degrades and we only do minor tactical bug fixes. Number 3, when you inherit an older system, program understanding is always the hardest phase of making a change. And number 4, understand exactly why emergency repairs are so dangerous. Remember, fixing source code directly causes your docs and code to fall out of sync, which severely threatens the long-term health of the entire system.
Listen, mastering software evolution is absolutely crucial because the reality is you'll likely spend the vast majority of your career maintaining existing systems, not writing shiny new programs from scratch. Which brings us to a really provocative thought for our next session. If we are spending 90% of our budget on evolution, how exactly do we manage aging legacy systems that have completely outlived their original hardware and the developers who built them? We're going to tackle the fascinating complexities of legacy software in our next explainer. Thanks so much for joining me today, and keep on learning.